So we saw the definition of current and its various form. Yeah, just started. So this is unbiased conductor. What is the meaning of unbiased? No potential difference has been applied. Okay. So we just have a piece of conductor, and you can think that okay, this is like a conductor with some high value of resistance compared to the other wire, and it is shown as a cylindrical object. So for the analysis of current and its various dependencies, we are going to start with the assumption that okay, the conductor is having uniform cross section, and from there we are going to derive all the formula. So let's say we have a conductor of finite cross section area and finite length also. The rest part is also conductor, but that is a pure conductor, which means it will have negligible resistance. I won't say zero resistance. So the idea is for pure conductor, the resistance is always tending to zero. It is negligible. It is not exactly zero. For a resistor, which is also a conductor, R is finite. So it is not zero, and for a superconductor, we know it is exactly zero. So these differentiation should be in the mind. And now we have a conductor. So we will talk about something called the electron C model. So inside the conductor, we have a large number of free electrons which are free to move. So they are free from the atoms of the lattice. I hope you know the lattice. So every conductor is having the crystalline structure. And the crystalline means it repeats certain geometrical pattern. That's called the crystalline. And in case of crystalline structure, what we have something called the unit cell. And the corners are generally occupied with the atoms. So we have corners which are predominantly occupied with atoms. So even a solid conductor will have some empty space. Now these empty spaces are not big enough to realize, but is small enough or you can say big enough, actually, big enough for the electron to move, or you can say roam freely. So generally what happens when God created this metal or metallic object, in the due process of creation, these atoms were brought very close to each other. And when the atoms are brought very close to each other, I mean, that's something beyond the discussion, but when you bring atoms very close, by virtue of some external work done by the God in creation, a lot of energy has been released because it is brought very, very close. And these atoms lost their electron. And these electrons are lost, means in a way you can say, uh, here we don't have individual atom. Okay, so I hope you know the individual atom follows the Bohr's theory, especially the single electron system. But when atoms are in cluster, it is not going to follow the Bohr's concept of atom. So what happens? The atom and their atomic orbitals, okay, they get intermixed, and because of the mixing of the atomic orbitals, instead of the fine energy levels which we generally see in case of discrete atoms, or you can say isolated atoms, we see some discrete energy levels. And I hope you know the Bohr's theory a bit about it. The metal or crystalline shape do not have the finite energy orbits. Rather, they have something called energy band, which means there is a range of energy in which the electron can live or move freely. So you can think this as a, like a, in case of a large apartment or some township, there are many buildings, and every building is not isolated, rather their roofs are connected. So you can go from one roof to another roof, and therefore you have a large area to play. Although you belong to one building, but when it comes to the roof, the roof is not discrete, rather it is interconnected. So what you get is a range of energy level. So you can draw the analogy from this idea that atoms, when come together, they create a range of energy level instead of the fine energy level, and such idea we call band theory of solids. So there is something called band theory of solids, because we have an energy band. Now, band theory of solids is a very important discussion when it comes to the world of semiconductor. But we should know only about, I mean, a basic about this. So according to the band theory, these atoms are interconnected, and now these electrons are left their individual atoms, but they haven't left the medium, which is the metal. So they are still free in a way, but still confined in another way. Confined means they are free to move within the rooftop, but they're not free to move in the entire, you can say, universe. So you give some freedom, but still you restrict it. And because of that, to give complete freedom, you need to give some more energy to those electrons who are, of course, in the rooftop playing there, not living in the room or flat. So those electrons which are free, moving in this lattice gap, or called the voids, they need certain more energy to leave the metal entirely or completely, and that energy we define as work function. So the whole idea of discussing this work function is so that you can understand what is exactly work function. You're free, but you are still not free. So work function is much, much lesser than energy of ionization. Why? Because in the due process of creation of metal itself, you have already left the atom. Okay. Now we cannot talk about the ionization energy because you are free from atom already. Okay. Yeah, we are not removing from the atom. We are going to remove the electrons from the surface of the metal, not from the atom of the metal. And the whole idea of discreteness or the fine energy levels will converge into idea of band, in which we have the energy range. Okay. And there are two types of band that we define in case of conductor. So for conductors, I'll only talk about the conductors. There are two types of band, and one is called the conduction band. Another is called the covalent band. So it is the conduction band, or not covalent, it's called valence band. Sorry, my bad. It's called valence band. So not all electrons participate in the conduction. So the conduction band is called the high energy band. Valence band is called the low energy band. And in the due creation of metal itself, the electron occupies different range of band. So first they try to fill the valence band, which is the low energy band, and once it is completely filled, so band is like of course you can think as a flat. So of course, I mean, you can live in let's say every person is given one room. So because we have finite number of rooms, so you can only occupy those finite numbers, and anything beyond that it has to go to the rooftop under the emergency situation, and that is why that rooftop can think as a conduction band, and they participate in conduction. Okay, so that is the band theory of solids. So in case of conductor, we have a large number of, we say, inexhaustible supply of free charge carriers. I'll write somewhere here. Inexhaustible supply of free charge carrier. No. So what they do is these free electrons, so as I said, the crystalline shapes are very compact. So the gap is very, very small, but it is big enough for the electron to move. So what happens? Why they move? They move because of their own kinetic energy, and that is called thermal energy. So in an unbiased conductor, I'll just put it in. So just in case of unbiased emitter, free electrons, also called conduction electrons, move in random fashion due to their own thermal energy. So any object, because we're talking about the medium or object, any object above the absolute zero temperature, which means I'm talking about the even more than 0 Kelvin, which is like more than 273.16 degrees Celsius. Everything which is above the absolute zero temperature will have some energy. Okay. And that kinetic energy is letting them to move in a random fashion. So if I draw the arrows for to show their movement, All will move in a random fashion, and we have no control. We don't have any control over how they decide to move. This is totally bizarre and random motion. So this is our kind of model. You can think that electrons are moving just like gas in a container. So that randomness can be mapped as per the kinetic theory of gases. And in fact, they do follow the same principle. So electron C model is basically a kinetic model. And we are free to apply the statistical ideas, which is prevalent for the kinetic theory of gases. So I'll come to that in a short time. So in case of unbiased conductor, these free electrons move in random fashion due to their own thermal energy, and they move particularly with the RMS velocity. Okay. So what is the RMS velocity? So you have studied in gases, it's a 3 RT by M capital M, but we write here as 3 KT by mass of electron. So to get a rough estimate of how fast they move, we call this as the VTH, the thermal velocity of electron. We call this as thermal velocity of electron. A simple calculation will reveal that this value is roughly equals to, I'll put the value, K is 1.38 into 10 power minus 23. Uh, absolute, I mean, the absolute temperature T, let's take the room temperature as 27 for the sake of writing. So this will be roughly how much, guys? 300 Kelvin. Okay. We are trying to understand a rough estimate for the electron's motion. And just and now let's put the mass. Mass is how much? 9.1. Because we are talking about the electrons, so we are not talking about the gases. And roughly, if you solve this, the rough estimate this turns out to be 10 to the power 5 meter per second. So you can imagine that a free electron is actually moving too fast, and they while they move freely for a very small distance because the dimensions are so small that they cannot move forever. So they make multiple collision with the lattice points called the atoms. They make collision with themselves also, which is very rare. I mean, generally electron have the lattice is acting as a disturbance to their motion. Okay. So these electrons are making collision, and therefore they do not move freely forever. So technically, one electron is roughly at their own place. You can imagine, if you imagine a nanometer dimension, so an electron will survive in that nanometer dimension, you can say nanometer radius sphere, and it is going to live there forever because of the collision from all directions. So symmetrically, all electrons will distribute in a way that you won't see a net motion. The motion is not there actually. So this is called localized motion. Everyone is moving locally, but there is no bulk transmission. There is no diffusion process taking place. And that is the reason if I draw a cross section here, if I draw a cross section here, how many electrons you think will cross this cross section from right to left and left to right? So in case of unbiased conductor, the number of electrons crossing from left to right is going to be roughly same as the number of electrons crossing from right to left. So the net cross section, I mean the net flow of charge is how much? So through this cross section, the net flow of charge is how much, guys? Zero. And that is why unbiased conductor fail to create current, although you can see these electrons are moving really fast. It's like 1 lakh meter per second. But even such a high speed is not capable of creating any current in the conductor. So unbiased conductor do not create current. So thermal velocity is not responsible for current creation. So what we need to know, the only one thing, that only one theoretical idea which we should be aware of, and that is thermal velocity do not contribute in current. Then exactly who creates the current? If thermal velocity, although having high value, but it fails to create any current, then the obvious question is who will create it? So to create current, we have to make a biased conductor. So we will draw again a conductor quickly. So the moment you bias means you apply a potential difference. You apply a potential difference means you create an electric field. So a battery is a symbolic to the idea of biasness. So now we'll talk about the bias conductor. So the moment you have a bias conductor, in a way you can think that this part is now kind of positively charged. This is like a negatively charged. And now this will create an electric field across the length of conductor. And see, the very purpose I kept the cross-sectional area uniform such that the field develop is also uniform. So later on, you will also come to know that for non-uniform cross-section, the field also becomes non-uniform. So this will create an electric field. Now, when you create a field, then naturally these free electrons, will they stop their thermal motion? What field will do? Will it stop the thermal motion? Yes or no? Tell me, guys. So the application of field is going to stop the thermal motion, or thermal motion will continue? What do you believe? It will definitely continue. And the presence of thermal motion will keep its randomness in place. So it is still random. But it is think like a situation. There is a crowd which is unruly crowd, and there is a lathi charge by the police. So now what will happen? The entire crowd will remain random, but still the crowd as a whole will shift in a direction of force. So if the, let's say the police force is coming from the right side, the crowd will as a whole shift towards left. Now, if you look inside the crowd, it is still random. But if you look at the crowd as a whole, that is the bigger picture. If you look crowd as a whole, then you can see the crowd as a whole will shift. And the idea that the bulk will shift or will move in a particular direction gave rise to the idea of or concept of something called drift velocity. So drift velocity is not meant for individual electrons. For individual electron, we only talk about the thermal velocity. So drift is like how my entire bulk, like the entire, if I take the entire segment of this wire, this conductor, and if you look at the entire tube as a whole, then these electrons as a whole will start shifting towards right. And as the entire electron will shift towards right, it will not create a vacuum. Rather, some other electron will be pushed back, and so you won't see the shift. What do you see? There is a sense of motion. It's like a fluidic motion, like a liquid. So as one liquid will go ahead, some other will come back from behind. And therefore, this will set up a flow. The bulk will start flow as a whole. You can think as a liquid model. And this flow we call drift velocity. The rate of this flow is called drift velocity. So drift is called a statistical parameter. So in case of bias conductor, what will happen? The randomness will remain same, but now if you draw a cross section and if you apply the theory of probability, so for electrons, we know the force will act on the left side because it's a negative charge particle. So field is right, electron is negative, force will be left, guys. Yes or no?
Yes.
So what will happen? That the chance of crossing this cross section from right to left and the left to right is not same. It is now biased, isn't it?
Yes.
So what we see now more often is that we have more on the left but less on the right. And now this difference, which is very small difference, is responsible for the net flow of charge through the cross section. Hence the concept of current. So current itself is nothing. It's a way of saying this event, that when there is a net flow of charge through the cross section of conductor, whenever this is established by some method, some arrangement, this state of charge is called current. So if someone will talk about what exactly is current, the answer is current itself is nothing. You are just saying when the bulk is in motion, you say that state as the current. That is how you're going to define the current. Okay. So is current something real? It's just like velocity. So we have a particle changing the position, and then because the position is changing with time, we are calling velocity. But what is more fundamental? Of course, I can say position is more fundamental than velocity. So we define mathematical definitions that the rate of change of this is this, this is this, this is this. Similarly, the charge is fundamental, and let's say motion is fundamental. And then given a cross section, when you count the net flow, and if it turns out to be non-zero, we say there is a current through the cross section. So this is the whole idea of current. And what is the role of a battery? The battery role is to create the field within the medium, and it is the field lines. You can think as, again, as a lines of force. Okay. It is the lines of force along which we are creating a fluid flow kind of situation. It's like a laminar flow. So if you look at the bulk, so now there is an idea of bulk, not the individual electron. The entire cluster of electron we refer to as a bulk, and the bulk will follow the streamline flow. Okay, not individual. Okay. So in case of bias conductor, what happens? The electrons will start moving slowly towards the right, and that will give the idea of drift velocity. And again, when someone is saying you drift velocity, always remember it is some sort of mathematical definition, nothing to do with the velocity and nothing to do with the individual electron. It has to do with the what? It has to do with
Bulk.
the bulk of the medium. Okay. So we cannot define family if a person is alone. Family means they are more than one, of course. So drift velocity is called statistical variable. So we need to know now three different statistical variables. Based on that, we are going to derive all the other formulas, which is part of this chapter. So the first variable that we define is called mean free path. And the same idea will also prevail in case of gases. There is no difference at all, because the kinetic model of gases, which we call kinetic theory of gases, and the electron C model follow the same mathematical principle called statistical physics. So we have something called so what is statistical physics? So it is a physics which is based on the theory of probability. Okay. So it is like a guesswork. Okay. And why such ideas are required to learn physics? The idea is we cannot deal with each and every electron in the bulk because it is just infinite number, and there is no mathematical way, or there is no supercomputer which is ever built which can deal with such a large number of variables and solve it. So you guys, when solve, I mean, two variable equation in two variable, you find it really difficult, and when you solve equation in three variable, you find super difficult. So imagine equation in 10 to the power 20 variable, or 10 to the power 40 or 30 variables. Can you imagine those equations? And do we have really a way to solve it? The answer is no. We do not have a way to solve it. Okay. So that is called a probabilistic idea or model of you can say some physical reality. So models are basically a mathematical idea of a physical reality. Mathematical idea of physical reality. So when you say Bohr's model, so it is just some thought from the someone's genius. Okay, like Niels Bohr thought about this model, and using that model he was able to explain to the world some physical reality. So it is not the real thing. Okay, so in no models is no model in the world are real. They are just close to mimic the physical reality. So that their purpose is to just somehow explain to you that why this reality is happening the way it is happening. Okay, but we also support with some experimental evidence. Then only it becomes a verifiable model. And every Nobel Prize which whoever has won, I mean, they are born, I mean, winning this prizes because of their own intuition about the physical reality. So they create their own intuition, and that is like a big success or breakthrough, and they get the Nobel Prize. So mean free path is what? So if we talk about a single electron, and if we just look at the randomness, I mean, the way they move, so they very much move in the Brownian motion. So before they make a collision and turn, they move straight. So this is called free path. This is called free path. Let's call free path as lambda 1. But the next free path may be slightly different. So we can call lambda 2. The next free path may be lambda 3, and so on. So mean free path is technically, it is sum of all the free path up to whatever number you want to continue. So this is called the mean free path. And mean free path is a physical model because it depends on, in a given volume, how many electrons are residing. So because if you expect a higher density, then definitely you will expect a lesser mean free path, isn't it? So more the crowd, lesser the free path to walk or run. So mean free path only depends on the charge carrier concentration. Okay, so we define that the lambda depends on charge carrier concentration, and more the concentration, lesser the lambda. So we can say as a lambda is, if if we call concentration as n, which we generally say, so as n will increase, lambda will decrease. I hope this is obvious thing, right?
Yes.
So this is the first thing called mean free path. And now comes the mean time of relaxation. Which we define by the symbol tau. So of course, to travel the distance, you will take some time, t1, and then you will travel something, t2. So this is called the this is called the free time, like time for which you travel. So now free time depends on how fast are you moving. Okay. So imagine you are moving really fast. The t1, t2 will be really small. And we know that when we say fast, then I mean, which velocity we talk about here? Thermal or drift? The mean time will depend on which velocity? The thermal velocity or the drift velocity?
Drift.
No, mean, when we talk about the mean values, we are talking about the individual motion of electron, right? How they
Okay.
move.
Yes. Okay.
So we talk about the individual, which means it is always the
Thermal.
thermal velocity. So what you need to understand that the mean free or mean time of relaxation is basically the mean free path upon thermal velocity. Okay. So generally you can also write as, and it can be written as lambda by V average or lambda by V RMS. It really doesn't matter. So all mathematical differences are roughly equivalent in terms of the order of magnitude. Okay. But what is more interesting here that if I talk about the proportionality, I mean, here we can write like this. If we talk about the proportionality, then lambda depends on inverse of concentration. That's logical thing. And thermal velocity depends on square root of temperature, isn't it?
Yes.
Do you realize this?
Yes. Yes.
Okay. In fact, later on you'll come to know that lambda having the exact expression equals to, for gases of course, root 2 pi d square n. So it is inversely proportional to n, and d is called diameter of the molecule. So bigger size objects will collide more frequently than a small size molecules. Electrons are very tiny, so I cannot write the exact formula what the dimension of electron, but we can say that this proportional relationship will also be valid in this case of electrons. So this is what you need to remember. This is from KTG, kinetic theory of gases. So tau is roughly, you can say tau is proportional to inverse of concentration and square root of temperature. So definitely as temperature will grow, they will move very fast. So they will make the frequent collision, and when they will make the frequent collision, then the mean time of relaxation will decrease. I hope this is clear to all of you.
Yes.
So so now we are good to go with the third definition called the drift velocity. Which we write as V subscript D. And again, before I explain what is this, I should mention here that this is a statistical parameter and is defined for bulk motion of electron, but not for individual motion. And you can also talk about the, so in case of gas, we do not talk about the drift. The reason is simple. In gas, we don't create a fan and talk about the how fast the wind is moving. But there we talk about the convection. Convection is similar to drift. Convection means how the entire medium is moving or flowing. Okay. So when you switch on the fan, the whole purpose of fan is to set the bulk of the wind, you can say the air, the bulk into motion, okay, by creating the pressure difference. So the wings of the fans are designed slightly tilted. You must have seen it is tilted. It is not flat, and it act as something like aerodynamics. So because of the shape of the wings, it creates pressure difference, which in turn sucks the air from bottom to top. And because of this commotion, or you can say convection established, you feel good. Okay, so you're getting the air actually. We also have the reversible fans in which they turn opposite, or maybe clockwise or anti-clockwise. They turn opposite, which in turn it sucks the air from bottom and create a vacuum. So you will get a less air or less windiness, which is used for the, if you want to use a fan during some, winter, you can use a reverse process. It's the same thing. Anyway, so drift velocity having a statistical definition, and the way we define is, so when you talk about the bulk, so before the application of the field, this bulk will have some velocity. And because they are large in number, so what is the on an average motion of the bulk? If I talk about this bulk, what is the on an average motion? So on an average, it is not moving at all, right? So the difference is how much? Zero. Because bulk is not motion. But the moment you make the biasness, okay, I'll just do like this. So when we have a bulk, and you can also see this event quite frequently if you have seen the uh, a large number of bees moving together, honeybee. Have you seen honeybee moving together? Anyone?
Yes. Yes.
So this is the honeybee. So they move randomly, but when you, let's say there is a wind moving in the direction, then the entire cluster will move together, and the rate at which the cluster will shift in the direction of applied field, let's say EVA field. So the rate at which this cluster will shift, keeping the randomness. So see, we are not going to affect the randomness. It is still random. So the rate at which this is shifting, this we call drift. So I hope the drift idea is clear. What is drift? So mathematically, drift velocity, drift velocity is the velocity acquired by electrons, is the average velocity acquired by electrons during one mean time of relaxation. Okay. Now the derivation, those who are reading SC Verma, for them, the derivation given in SC Verma is not as per the JEE. It is not wrong. It is not right. It is just not as per NCERT. So Vermaji has used a definition which is generally given by the Russian authors, but we are going to follow the Resnick-Halliday derivation with slight difference. The difference is only in terms of some coefficient, and the actual derivation is beyond the scope of JEE and BSc degree. Okay. And later on, we'll come to know that there's nothing like current, nothing like, I mean, there's nothing like nothing. I mean, everything you're going to study is not going to exist anywhere once you do the higher studies. Okay. Anyway. So do not follow the derivation of Hesselhoff. That's it. Follow my derivation. So Verma has also clarified in one of his videos that okay, all derivations are equal. It is just the model, and therefore you have some assumption. And I found a book in which Verma's derivation was also there. So he got inspiration made from the one of the Russian author. Okay. So anyway, that is not our concern. So if I apply the, I think about the electron under the influence of electric field. So this electron will experience the force in which direction, guys? Left, right?
Yes.
So we can add the force on electron equals to charge into electric field, isn't it?
Yes.
Yes.
So a constant field will have constant force, isn't it?
Yeah.
And therefore, if I find the acceleration vector, so acceleration is something which is unique for every electron, isn't it? Because acceleration depends on force applied, and because every electron, every electron, no matter what or which electron we talk about in the entire bulk, every electron is under the same field, so we'll experience same force, so we'll have same acceleration. Do you realize this? So when we
Yes.
talk about
Yes.
the velocity v equals to u plus at, and if we take the average value, so we write as v vector and the average of Luckily, A is same for all. So if something is constant, so average will be same value. And what we need to understand or know that the U is the initial velocity before you applied the field, and it was so random that on an average this turns out to be zero. Do you realize this? So if
Yes.
one electron is going
Yeah.
right, there must be some electron in the bulk which is going left. If one going this way, then I can always guess that there must be some going this way. Why? Because the number is infinite. Okay, number is infinite. You can think of any crowd and imagine that every event will have some reciprocal event happening. Okay. And therefore, the A is constant, so we can take it out, and the average of T we call tau. So we take as tau, not call, we take as tau, the mean time of relaxation. And this term we call drift velocity. So this is the formula we are going to use for drift velocity. The V drift is A tau. I hope this part is clear because this is the most crucial stage. Beyond this, we have all the mathematical formula that we are going to witness today. So if you're okay with this part, you can realize that even though we are learning a chapter called current and electricity, but we are still applying the very basic idea of laws of motion, isn't it? Kinematics.
Yeah.
Because current is a state and we define current for electrons. So you can think electrons as a physical quantity or physical entity having the property, I mean, like they have charge, and because they are moving through a cross section, so they constitute a moving state of charge, which we prefer to call current. Okay. So now the world is sorted. Now you can understand that it is still the same old kinetic energy, same old potential, same, and now the entire world is same old thing, the way we have seen in mechanics. Okay. So that is why I say you have to only understand mechanics, the rest is cosmetic. So in physics, we don't have any chapter actually. We just have some cosmetic changes, some definition, some new model of interpretation, and things are very simple if you know basic. So the drift velocity we write as a tau, and if I write in magnitude, so now we can write. So this is the formula where I start the future derivation. This is the formula that we must understand how it is written. It is very simple. It is simply v equals to u plus at. And I hope you know how to write a and just replace t by tau, which is the mean time of relaxation. So in this particular, guys,
Yes.
Yes.
so now you know how the bulk will move, right? What you know? How the bulk will move. So if I choose, let n be the concentration of free charge carrier. In case of conductor, we have only one free charge carrier, and that is electron, right? And we talk about which electron? Conduction electrons. And conduction electrons are free from the atom, but not free from the medium. Just So in case of conductor, we just have electrons. So n is, and n is such a quantity which can be derived very easily. So how to derive n? Imagine any metal. So it may be gold, silver, or no, it's like copper. Anyway. So if we have a metal, take any part of it, any small part of mass. For every metal, we know the molar mass. So what will be the number of atoms in the DM, or what is the number of moles? Number of moles in a DM mass equals to how much? Tell me, guys.
dmn upon n.
DM upon A. That's it.
But oh,
See, we are talking about moles.
yes, yes, huh.
So number of atoms will be how much? In one mole, how many atoms?
Avogadro constant. N.
Avogadro constant. So we cannot DM by M into N. Is this clear so far?
Yes.
Let's say the valency of atom is X, because valency can be 1, 2, or 3, right? Because for atoms, for metallic atoms, metal can generally give how many electrons? 1, 2, or 3, right?
Yes.
If every atom, or if each atom in the crystal will donate 1 electron, then can we say the entire volume of conductor will have exactly same number of free electrons as the number of atoms? Can we say? So let's say if a copper undergoes Cu++ and it releases 2 electrons. So in such metal in which we have to believe this is the true equation, the number of electron will be how much? Twice the number of atoms? Yes or no?
Yes.
So if I continue this, so number of free electrons will be equals to or equivalent of how much? Mole. It's very easy. Mole, Avogadro, valency. Is this clear, guys?
Yes.
So N is defined as number of free electrons per unit volume. Okay. What do we define? Number of electrons per unit volume, and therefore this will become dm by m nax by d volume, which we can write as mass upon volume into Avogadro number into valency upon molar mass. And we all know mass upon volume is called density. So some book they use the density as d, so it's easy to remember dna by mx. And that is why I said n is a predefined quantity. So n is something which is known to us because of the physical property. So the physical property of the material or medium or conductor will decide the value of n. I hope this is clear. And
Yes.
you all can derive
Yes, sir.
on your own. In case if you forgot, don't worry. Derive from the basic. Now let me tell you, this chapter will have just too many formulas. Now you may ask, is it easy to remember? The answer is no. I never, I mean, even as a student, I was never able to understand or remember anything. But I was knowing all derivation with ease. So I could derive the entire chapter formula within 3 to 5 minutes. So for you also, I'm saying, suggesting that you're also going to forget formulas. So just learn the way of derivation. It is hard to remember the formula. Even if you remember, you're going to miss it in the examination. So it's good to derive. And through derivation, if you remember, you will remember forever. So after some practice through derivation, that formula will be part of your brain, I mean memory actually. Okay, so coming to the drift velocity, the first derivation, concentration is a predefined value which is generally given to us. And these two values are going to help us in deriving everything else. So now we are going to do the derivation of current through biased cylindrical conductor. So what is the benefit of bias? I mean, bias means we have a source of voltage, right? Potential difference, correct?
Yes.
And the cylindrical will make sure that the field is going to be uniform, right? Isn't it? Which
Yeah.
color will go for this color? Yeah, this is no. Okay. Orange goes with. So I'll work on my color combination skills. So we keep the cross section area constant. L is the length. And now when we talk about the bulk motion, so bulk motion is called drift velocity, right? So imagine a cross section. And so derivation of current through biased cylindrical connector. Although it's not required, but it's good to know there's something called steady state derivation. So let me talk about the before I derive finally. Just in a brief, I'll talk about the steady state. Or equilibrium state. So what is the steady state or equilibrium state? I said that the number of electrons is n. Okay. The steady state will confirm or will ascertain that the concentration is not only meant for the bulk, but even if you choose a small piece of it, and if you try to obtain n there, that n should match with every other n which you can possibly derive from other volume. Which means if you take a conductor and if you cut into infinite elementary pieces, and if each piece is going to give you the same value of concentration, it means the charge distribution is in equilibrium. So that is the meaning of steady state here. So I just put in, so steady state in case of conductor talks about charge concentration equilibrium, that is if some electron will leave any volume, then same number must enter that volume to keep the concentration constant. Yeah, I hope it's clear. So are you getting the idea of steady state? I want to make sure that the number of electrons in every volume is same. Okay. So when the bulk motion is the beauty of bulk motion is when the motion moves as a bulk, their internal configuration remains same in steady state. So they move as a whole, but their internal separation, mean free path, and all those things remain same. And they move in such a way that okay, if some part is leaving, then some part is getting occupied by somebody else. Okay. So in a way, if I draw two cross section, just imagine, just take two random cross section. Just take. Now imagine the cylinder between this cross section. And this is very, very important idea. So let's say if some electron is entering this cross section, and imagine the other cross section which I am drawing on the right side, dn dash is leaving, and let's say dn dash is less than dn. What does it mean? This volume will have extra electron than before, yes or no?
Yes.
Yes.
Which means it is not the steady state. In steady state, you cannot change the concentration of a given volume. Now, when the steady state is possible, when
That is
the dn here and dn here are, so whatever is entering from this cross section, the same must leave from here also, yes or no?
Yes.
Yeah.
If I draw a cross section somewhere here, beyond that also, you can further do the similar idea that whatever is entering this volume, the new cylinder, the same must be living here, right?
yes.
Now, if I draw any cross section, all will witness what? Same number of electron crossing the cross section, isn't it? Yes or no?
Yes.
Now, the beauty of a steady state is that because every cross section will witness the same answer, same electron crossing, same time, in the same time, then every cross section will give you the same current value, isn't it?
Yeah.
Because I said current is defined for cross section, and what you can see that in steady state, every cross section says the same answer, isn't it? And because every cross section is saying the same answer, can we conclude that current is constant? Can we?
Yes.
So can we conclude that the current is flowing through the medium is constant? Can we? So it is this case where we say current through the medium. Otherwise, we must say current through the cross section. So when you say a current of 2 ampere is flowing through a wire, what do you mean by that statement? You mean that no matter which cross section you choose, you will witness 2 ampere per second. That is the meaning. I hope all of you are able to realize this fact, which I discussed in the very first lecture.
Yeah.
So current is defined for cross section, but we can say it for medium only when it is steady state flow, because in steady state, no matter which cross section you draw, you are going to get the same answer. Okay, guys, is this clear?
Yes.
Yes.
Okay. So therefore, if I draw a cross section which is not what you mean, like not uniform, You know what will happen if I have a conductor of this shape? If I have a conductor of this shape, so going by the same idea of electrostatics, if I say this is positively charged, let's say some battery is there, which I'm not showing. The field lines will be no longer the way they used to be. So field lines are going to be something like this. Is this clear? The lines of force will have a different orientation. So if you come at any cross section, now you may think that a bigger cross section may have bigger current, but the answer is no. If I choose any two cross section between any two region, if I talk about these two cross section, so if I talk about these two cross section between as per the idea of steady state, whatever number will enter from here, the same must exit from here. Yes or no? Because if this will not happen, what will happen? The number of electron in this volume will grow with time or shrink with time,
Yeah.
which is the violation of steady state. No?
Hmm.
So even though you make a bigger cross section, you will not get a larger current. Rather, you get the same current. And if you want to go much deeper, why it is happening, then go deeper. That's not an issue. So if I draw a bigger and a smaller, try to understand the direction of electric field at these 2 points. So at this point, it is slightly tilted, but at this point, it is like this. Now, if I make the angle, let's say this is alpha, this is beta. The field here is like this, the field here is like this. Okay. In fact, this field is weaker because as the lines of force will flare away or spread out, the field becomes weaker, right? Now, the one which is responsible for the drift is the beta, the component along the flow, which is E dash cos beta. And here we have E cos alpha. So there are two stages. First, E dash is lesser in value and beta is bigger. So E dash cos beta is much, much less than E cos alpha. And second, the drift velocity at this junction, if I call VD, and if the drift velocity at this junction is called VD dash, here the drift will be much lesser than the drift here. So what will happen if you look at the idea, a bigger cross section and the lower drift will maintain the same current as the lower cross section and bigger drift, because we want to keep the number of electrons or number of charge crossing the cross section per unit time constant. So there are two ways. If you have less small area, then you move fast, isn't it? And if you have big area, then you move slow. In that way, you can going to maintain the number of electrons crossing per unit time, and that is how you maintain the current same throughout. So in steady state, what we need to remember, in steady state, current is a constant quantity, and that is true irrespective of the shape of the conductor. So I'll put this as the takeaway point. So current in steady state condition remains same or remains constant irrespective of shape of conductor. Okay. So when you have a random shape object, the current is established due to the motion of the bulk following the electric field lines. Okay. So first of all, the battery is a source of creation of the field lines. I mean, that creates the potential difference, and which in turn creates the field, and that field lines will is something which the bulk follows, and eventually they move along the flow. So all this idea will come as a mathematical formula in this chapter, which you are going to see today itself. So now we are looking for derivation, right? What I said, derivation of current. Okay. Uh, Derivation of current. Now, when I'm going to derive, always remember when your teacher is deriving something on a board, it is mandatory to know that under what condition the derivation is obtained. So the application of a formula is only true when that
Conditions.
context, yeah, that context is also matching. It is not just a formula. So if you follow a formula blindly, there is a high chance you will commit a mistake. More than formula, I always emphasize this, and I keep on saying this again and again. More than formula, always try to remember under what set of conditions the formula was derived, and the condition in which it was derived will also limit its applicability. And when you see a different context, you need to go to the basic. That's called derivation method. Okay. Anyway, so we have been talking about this for a long time, and time and again I keep on repeating this so that you can keep this fact in your mind while you solve it. Okay. So we have A, L, V. The parameter that we would like to express our answer with is N. And we also going to use the idea of drift velocity Vd as a derivational parameter. And to derive it is very easy because the bulk is moving with the drift velocity. So in time dt, how much the bulk will travel? Can you guess? If Vd is the drift velocity, guys, then in time dt, how much will travel? So you can say that, okay, the entire volume of Vd dt is now been replaced by some new, you can say electrons, right? Because it is a flow.
Yeah.
So this volume you have replaced, no? And the previously prevailing electron in this volume has now moved forward. So to calculate how many electron has crossed this cross section, we just need to know this volume, and n is the concentration, so we can get the exact number of charges crossing this area, and then we can find the current easily. So tell me, guys, first of all, what is the volume shift in time dt?
A into VDD.
So this is the volume shift. So how many charge carriers has crossed this cross section? Can we say it is the same charge which were living in that volume? So can we say dn equals to? So we know dn by d volume is called n concentration.
Yes.
So dn is called.
N into the.
So can we write dn equals to n into a into vd into dt? Yes or no?
Yes.
Yeah.
And every electron carries charge E. The total charge carried by the electron while crossing the cross section in time dt will be the electron count into charge. Yes or no?
Yes.
Yes, sir.
I think this is very logical, not very difficult. So we can write answers NAVD into dt into. And what is the definition of current? Because in steady state I is constant, so we can write I equals to dq by dt or delta q by delta t because it's constant. It really doesn't matter.
Yeah.
And if you look from this equation, what is the value of dq by dt, guys?
NEEVD.
See, done. Imagine we are getting the current in terms of laws of motion because eventually this is physical parameter. This is the God gifted parameter, which is again called physical parameter. This is called geometrical parameter because you decide how big the cross section is. And the VD, if you remember, what was the VD? VD when we derived, imagine it is the acceleration and time. So it's just so many things going on, right? When we derive something, if you look at the very basic of it, it's very simple. You can realize that how things came to being actually. Okay. I hope this is clear.
Yes, sir.
Any doubt, guys?
Yes, sir.
All right. So the current formula is clear. So we got the current answer I equals to. Now remember this I equals to NEAVD. Tell me I equals to NEAVD. I equals to NEAVD. Everyone. Yeah. I equals to
NE.
NEEVD.
I equals to
NEEVD.
I equals to
NE.
everyone. Say it loud. I equals to.
NEEVD.
I'm not saying say Jai Mata Ki. I'm saying just say it loud. I equals to.
NEEVD.
So remember this formula. Okay. I equals to. I equals to.
NE.
Don't abuse me. Okay. It's okay. I'm stopping it. So I equals to last one last.
NE.
Okay. So I hope this is done. So generally what happens if you know drift you can find, but the opposite happens. So in experiment, if you have some device called a meter, you can find I actually. Okay. N is a physical quantity as I have given the formula. So we find the drift velocity. So every statistical parameter can be experimentally verified. That is the whole idea behind. So let's say I create a theory. Okay, I create a theory, and then from the theory, I calculate the value of the drift using the uh, experiment. So this is the reading of a meter. This we know, and this is of course we know. And if this value which we derived experimentally is matching my statistical model value, where is that? Yeah. If both will match together, then I can say my model is accurate, my model is correct. Yes or no?
Yes.
So every model should be experimentally verifiable, and if it is not, we don't call it a model. So you guess a model, you design a model, and then you try to predict the behavior, and then through experiment you try to justify the behavior, and when both will match, then the models are accepted, and once it is accepted, then congratulations, you will win the Nobel Prize. So it's very easy to get the Nobel Prize, isn't it? Oh, it's difficult to find the model, nevertheless. So now we are going to derive something called derivation of, I'll put in bracket this part. This is done. Okay, let's me put something more. I'll put a like box model. So every formula should look separately. Change of color. So we define something called current density. Now, when I say density, what comes to your mind? Density, what comes to your mind?
Something per unit volume.
Yeah, so there is a problem. That's the problem actually in the world. Something per unit volume is called volume density. So density is a very generic word. Okay. And since our childhood, in the name of density, what we have studied is only volume density. So we have somehow believed that density means something per unit volume. Let's break the stereotype. Density is a generic term. So we have population density, which we have been studying since our childhood. Maybe when in the geography class, you might have heard about the population density, or in the ecology, okay, something like that. So we have a density in electro. We saw surface charge density. So we define density over a surface. You define density over the length. We call linear charge density. We do have linear mass density. We have surface mass density, and we do have volume mass density, or which we by default call density. So density is a generic word. You must understand the density from the context. Don't apply something current volume. So when I am asking current density, you all tell. Current is defined for what? Volume or for area? Tell me common sense.
Area.
Area.
So current is defined for cross section, na?
Yeah.
Yes.
So when I say a current of I ampere flowing through a wire, then wire will have some cross section which we don't know. And through the entire cross section, that current is actually measured. So when I'm saying current density, I'm talking about current per unit what?
Area.
Volume or area
Area.
Area.
or length.
Area.
Area.
So that is how we should understand. Okay, the context is boss. We all must respect the context. If you don't respect, you will make mistake. So current density is defined as current per unit area. Okay. And because why we are writing here, because we know that we are deriving for the the cylindrical wire, and there the I was uniformly distributed, because the field is, if you look at the field lines, when the field lines are uniform, the current will be also uniform, isn't it? And that is why the formula you can see is very simple to understand. It's Ne. Now current we define for the entire cross section. What about I? I we define for? Sorry, J we define for J. It is for the entire cross section, or is it for the a point of cross section?
Per unit cross section.
So per unit cross section is basically like a point. We
Yeah.
talk about a point which is dimensionless. Okay.
Yes.
Now imagine those diagrams which I have drawn so far. If you look at one point, can you see a unique direction of field lines?
Yeah.
At one point of cross section, can we say the field lines will have unique direction? Yes or no?
Yes.
Yes.
But if you look at the entire cross section, can we say that every case will have unique direction?
No.
If you look at the cylinder, you can say, yeah, for cylinder it is same direction. But the moment we switch from cylinder to other shape, do you see the field lines in a similar fashion?
No.
So for the bigger cross section and planar, and when the field lines are not uniform. So if a cross section is having non-uniform field lines, then current density at every point will vary. Yes or no? In a way, if I take the same cross section and if I cut into small pieces, small patches like polka dots, then every tiny polka dot will have same current or different current if it is non-uniform.
Different.
Different common sense. So current density is a point property, current is a surface property. Understood? And because of the uniqueness of current density, it is a vector quantity. Current is a scalar because there is no unique direction. Current density is a vector because it is unique in nature. So the first thing that we need to learn that current density is a vector quantity. It is a vector quantity. I hope this is clear. Why it is vector? Huh?
Yes.
Yes.
Current is scalar. Current cannot be vector. And in fact, current density is called tensor. In more generic sense, it is tensor. So in International Physics Olympiad, there was a question of current density, which we were supposed to solve using the idea of tensor idea. I mean, not difficult, but it's not easy for not at all for any beginner. So it is a vector quantity. You keep as a a vector. Tensor is too much. So J is NEVD. And if you look back at VD, can you go back and mentally and recatch the formula of VD? What is the formula of VD? The first derivation. Can you recall the formula? Anyone?
Yes, sir.
Tell me.
It's E by ME into relaxation time down.
Very good. Excellent. So the VD inherently, if you look at the formula, the original formula, it was a vector quantity, isn't it? The VD is the velocity. I mean, in that context, so VD was a vector quantity, and it depends on the electric field vector, right? If you look at the formula,
Yes.
are you guys able to see that formula closely, mentally?
So,
So drift velocity itself is a vector quantity, and because J depends on VD, so it automatically becomes a vector. But even if you look more inside, you will see, oh my God, everything is electric field. VD or J, the end result is it is connected with electric field, no? And because electric field is vector, so these are vector quantities. Yes or no?
yes.
I hope this is clear to all of you.
Yes, sir.
So J equals to NEVD, J equals to NE, I equals to NEAVD, so J equals to NEVD. Okay. So these two formulas are very, very important, and now we go to something called a relation between current and current density. Now this is very, very crucial. Why? For the chapter of magnetism called Ampere's circuital law. So there you need to know a lot about this. So imagine we have a cross section. I'm just drawing the cross sectional view of some current carrying wire. So it is meaningless for me to not to draw the every conductor and all. So imagine this is the what I'll say
Cross-section.
cross sectional view of current carrying conductor of circular cross section. Yeah. Is it required? I mean, that's okay. I think this is fine. So from the context, you can understand what I'm saying. Okay. And now, this is the capital radius. And let's say G, I mean, sorry, G, not G, the current is varying over the surface with some function. Okay. So current, when we define for the entire cross section. And if it is not uniform, then we have to add equals to J vector dot area vector. That's it. It is J dot D. J dot D. So here we have flat surface. Is it necessary that we will always get the flat surface? The answer is no. We can get curved surface also. Okay. So imagine we have a conductor of spherical shape. Okay. Yes, imagine. And somehow, the logic, don't ask me the logic, but somehow the current is flowing from the inner surface. It's a hollow spherical conductor. It's a hollow from inside. And current is moving from the inner surface towards the outer surface. Imagine the way electrons are moving. They are moving radially away. They are moving radially away. So if you want to cover the entire electron, what kind of surface you must draw? Electrons are moving from inner surface towards the outer surface in a radial direction. So if you are at some intermediate position, the cross section through which the electrons are crossing is of what shape? Is it flat or is it curved? I mean, what kind of curve it is? Like electrons are moving radially away. Okay, let me draw this. So we have medium here. We have medium here, and this is how the current is flowing. So as you go away from the inner surface to outer surface, the cross-sectional area will increase, decrease, remain same. Cross-section, you know what is the cross-section? It is the surface perpendicular to the motion of the current. I mean, motion means the flow of current. So if you draw a cross-section here, how it will look like? Can you guess? Pardon?
I think it will be like flat.
It will like a. I mean,
Flat.
see, common sense. You have inner surface, you have outer surface. You're going, current is going from inner to outer. How it will move?
Reading outwards.
So the cross section you're crossing is constant or changing.
I think it's constant.
Okay, it means you're not able to imagine. So none of you are able to imagine. Until you cannot imagine, you cannot solve question. It's common sense. I mean, inner surface, outer surface, current is moving. How current is moving? Radially away. So as you go away, you cross bigger and bigger area. Na?
Yeah.
It's a spherical. Okay, not getting it. Still not getting it. Imagine you're trying to cross the outer surface. Is the outer surface and inner surface same area? Hmm? No. Still none of you are getting it. Okay, no. You're not able to realize that, okay, this is the flat surface. What I drew was the spherical surface. Are you guys getting it? What I'm saying? A big sphere, make a hollow. So they say this is at high potential, this is at low potential. And now current is moving this way. So while crossing the inner, while going from inner to outer surface, the area of cross section through which the charge will cross is constant or variable.
Variable.
So what kind of area you are getting here?
Spherical.
It is concentric sphere, exactly.
Yes.
And as you move away, the radius of the sphere will increase.
Yes.
So as you go from inner to the outer surface, do you realize that you are going through bigger and bigger cross section?
Yes.
So as you go from inner to outer, the cross section will grow in value. So to maintain the constant current, what must decrease? Because the current is same, na? I think we all are not on the same page. What I'm saying and what I'm understanding is not concurrent. Tell me what you are not getting it. Are you not getting my question? Are you not able to visualize the flow? Imagine the surface is, let's say surface is having 100 electrons uniformly sitting over the surface. They all start moving readily away. So the charge number is only 100 now. Okay. and that same 100 will go further and further and further. So what cross section we cross to go next? Do you realize this? No.
Yes.
So how many of you are able to realize this? No. I can clearly see it is a spherical surface. Why are you not able to see? I'm not able to comprehend. You can explain what happened to your thought process. So as the electron will move readily away, the area which will cross is same or different? Do you realize the area? Yes or no?
Yes.
Yes.
You're crossing the surface, no? Yes or no?
Yeah.
So the surface is growing in area or shrinking in area or remaining constant if you move. Huh? Tell me, guys, please. As you go from inner to outer surface, the cross-sectional area is same or different.
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 Can you explain what kind of different? I mean, how it
It's
is
increasing.
It's improving. Increasing.
and what shape the surface is having, the which you're crossing.
Spherical.
Similarly, if we have a cylindrical object, hollow cylinder, in which we have the inner surface, outer surface, and if the electron is moving radially away, then as you move away, the cross section will again increase or decrease or remain same. You have to understand the flow of direction of electron. I mean, how the current is moving. So here the cross section is increasing for a cylindrical object like this. See, I have done infinite cylinder many times in this whole course. You should be able to realize what when I say cylinder. Are you not able to imagine this shape? Is it so difficult?
No.
Let's see if I put this at high potential, this at low potential.
Again,
So as you move
Increasing.
away, it will increase. Yes or no?
Yes.
Yes.
So do you realize the shape of surface area for every current flow? In case of plane conductor, in case of cylindrical conductor, how the current is moving this way, no?
Yeah.
Yes.
So here the area of cross section is same or constant or different. Is it varying?
No.
In the direction of flow, is the area same?
Yes.
Yeah.
Yeah, here area is same.
Yes.
The first step of learning this chapter is that you must understand the concept of area. And as per the flow direction, you must understand whether the area is varying or is constant. Okay.
Yes.
Anyway, so we are going to derive. So we got I equals to NEA VD, and then we got VD equals to I by NEA, and then we got J equals to NE VD. And what I'm saying, the current and current density relation is very simple. It is J dot dA. So luckily in this case, the J, if I choose J to be inward, and dA vector if I take also inward because it's open surface, then J dot dA will be how much, guys? The angle between J vector and dA vector will be 0, isn't it?
Yes.
So the current we write as J dot dA. So which you can, in this case, you can write as
J.
simply J integration J. And if J is also constant, you can take it out. If it is variable, you can keep it inside. So let's do one problem just to use the formula, then we can go to the next concept. So I equals to use application. J dA or J dot dA. And let's say if I give you, I mean, for a flat surface, if I give you a flat surface, flat So for flat surface, what we know? If I give j equals to j naught 1 minus r by r, and this is of course only true when r is less than or equal to r. Can you find the total current through the entire cross section? So can you guys solve it and tell me the answer?
Yes.
You can clearly understand j is varying as per the radius, r is the distance from center. So this is your, and we have done derivations like this. You should know how to take elementary, how to find the current and get the answer. So the question is clear to all of you, or are you having doubt in the question itself? Tell me.
You.
Clear, no? Please go ahead and solve this. Everyone, please. And those who are having doubt, raise your hand. I'll explain again. Not an issue. Archit, Garv, Tanu, Prasiv, Manasvi, Manav, Mugdha, and Tanish. Anyone having doubt, you can raise your hand. So those who want to ask but not in front of all, you can message me.
Got the answer.
Just. So what is the answer?
J naught R cube pi by 3.
J naught R cube pi by 3. This much?
Yes.
Fine. Anybody else getting the answer? Receive. Tell me the answer.
Yes, sir. I'm getting safe.
Okay. You all should get the answer. You know how to take elementary. We have been taking elementary since ages. And these all are routine process. It's like once you learn, just repetition. If you ask me what we have learned so far in this chapter, there are only two things: tau and lambda, and drift. The rest are simply manipulation part. You have to manipulate to get other answers.
Hello.
Yeah.
Sir, this is not correct answer.
Okay. Then the other answer.
So one.
Okay. Anyone tell me what is the DA you have got? What is the DA here? So J is a function of R. So the locus will be locus. What is locus? Something with constant R, which is the circle. And then you move further dr.
2 pi r dr.
And now what you do, you find the current through this elementary area because that J is constant for this part. Do you realize this? J is constant here.
Yes.
Yes, sir.
See, your percent J is R function, so I should go R cut dr because in that dr, the J is almost constant. So we can write as
2 pi r dr. Yes.
the current through that element is J into dA. It's a flat surface, we can add J dA always. And J is J not. So the dI is 2 pi J not constant and R minus R square by R into
Yes.
dr. So the total current is which is I think R square by 6, no?
Yes, so that only. Sorry.
It is R square by 6. So okay, R cube is not the R square.
Yes, yes, that only.
The answer is correct.
Yes.
So this is not a big deal. Okay. For any medium in a steady state, what remains constant? What remains constant? Current remains constant, right?
Yes.
So even though J is variable, what will remain same?
Current.
Current remains. I remains constant for any steady state. So imagine if I give you a spherical surface. So imagine we have a conductor with a spherical surface. So if it is a spherical conductor, and imagine current is moving away from it. So current is moving. So at a distance R, let's say I is the current. And I imagine the current is readily outward. Imagine. It's only matter of imagination. So if I draw a concentric sphere of radius small r, what will be the current density at this point? What is J here? So J is going to be same everywhere because it's spreading in a symmetrical fashion. So what is the current density at a distance r? So consider current flow in radially outward direction. Find current density. as a function of these guys. Tell me. Yeah,
That the I is given.
given. Yeah, given. So when you reach r distance away, what area you are supposed to cross now? You are supposed to cross how much area? We have done this in Gauss law. Come on, guys. It's 4 points, but that's it.
Aspirants.
This is the answer. Similarly, if I draw something like this, this is the something fundamentally, I mean, we all should know, then only we can solve some of the challenging problems. So imagine the current is moving readily away. So find the J as a function of R. Length. Current density will be how much? Tell me.
I by 2 pi r.
Just okay. So this is, I think this is Simple. Okay, you can apply anywhere. So as you go from inner surface to outer surface, I remains same, but current density will keep on decreasing. Okay, so anyway, this is the basic practice about the formula and current density. The two things are done. So quickly, I'm going to derive a large number of formula. So the first one is called, okay, let's call it derivation of Ohm's law. Derivation of Ohm's law. So we know J is defined as NEVD. Okay. And we know, okay, we can start from always J, that's very easy. So let's say J is defined as NEVD and VD is defined as EE by ME tau.
Yes.
So always keep these two formulas in mind. The rest will be easy on your brain. Okay. So don't try to mug up every formula when it's going to be a large. So now what you can do next, replace it. So once you replace J becomes what? NE EE tau. And of course, I mean, I don't expect that anyone will remember this. So J turns out to be how much? NE square tau by ME whole into E. Okay. So this is the formula that J is NE is now N is what? Physical parameter. E is a universal constant. Of course, we know tau is statistical parameter. ME is the mass of electron. So N is constant. For a metal, N is generally constant. The E and ME are constant. And tau is a temperature dependence quantity. Do you realize this? Yes or no?
Yes.
Yes.
Yes, sir.
You have to go back to basic to understand everything. See, that's the problem with this chapter. What you're learning is the most difficult part of the chapter. The rest is like piece of cake. So 90% of the chapter is very easy. Only 10% is difficult. This entire term we call conductivity of metal. And we represent by the symbol sigma. And again, it's a matter of convenience, nothing else. So writing this bulky thing is not good. So we write as J equals to sigma. So this is the famous Ohm's law. Oh, you don't know this law. This is called local form of Ohm's law. So what is the meaning of local form? Local means it is a point defined relationship. So you will come to know very soon that V equals to IR also. But that is called global Ohm's law, which means you write it for two terminal, or you can say two ends or 2 points. So in the local form of Ohm's law, it's purely vector representation. So we write as, or you can write as J vector is sigma into E vector. So sigma is definitely a scalar, but E is a vector. And that is why J is a vector. So J equals to sigma is actually Ohm's law. This is Ohm's law actually. And if you want, you can also write as E equals to J by sigma. Again, matter of convenience. So 1 by sigma we call resistivity. Inverse of conductivity we write as resistivity, rho symbol. And that is why the E we can write in terms of resistivity, rho J. Okay. Understood.
Yes, sir.
And this leads to another formula that I equals to, if you remember, it is J dot dA And now it turns out to be J itself is sigma E dot dA, and therefore sigma is a constant quantity. Let's say if sigma is constant, so let sigma is constant, I equals to E dot dA, and this is the exactly the flux through the surface. So current is sigma into flux. If you know the cross section, if you know the flux through the cross section, you can easily find the current also, knowing the resistivity of the medium. Okay.
Yes.
And there comes the another form of the flux is then equals to I upon sigma, which is again like rho into I. Oh my God, so much. So you can imagine we are not supposed to know every formula. We are supposed to know how to derive it and how to do the manipulation to get one in terms of other and vice versa, because we really do not know how the questions are going to be, I mean, coming in the examination. So which one is the right format to do to begin with, we don't. Okay. All right. So that's pretty easy, I think. I equals to, that's so such a nice formula, sigma rho. So so let's derive the Ohm's law in the context of a cylindrical conductor. Of course, we can derive for other, but that's difficult. Let's begin with cylindrical conductor. That is the first choice. Huh? So this is a voltage V. So this will create a potential difference across this. For a uniform cross section, when the field lines are constant in value, we can directly write the relationship between electric field and potential, isn't it? So what is the relationship between E, V, and L?
E is equal to V into
Equal
E equals to
V into L.
V into L.
V.
Think about it. Think about it. What is the relationship between potential and field? You know the potential difference, you know the separation. What is the E then?
V dot.
Huh? Say it loud again.
V dot.
V dot. What is V dot? Come on. Electrostatics. The electric field is defined as potential difference upon separation. Okay, sorry. So E equals to V by L. Anyone having doubt in this formula? So simple formula.
No.
जो guys are forgetting, huh? So knowledge is volatile. Huh? Knowledge is highly volatile. So keep on revising. So now the good thing is the J we write is sigma into, or you can say E equals to E is rho J. Okay, I can derive from it. But we can also write E equals to and J we can write as I by what? A. So V turns out to be how much? Rho L by A. And this rho L by A we prefer to call, again, nothing like this. You can call anything, but we prefer to call R, which means resistance of conductor. So the simple thing is the V equals to Ri. We can derive from basic, and this is called global form of Ohm's law, which you generally call Ohm's law, right? Like in high school, this is what was taught to us. Even now it's knowing the same. So R now is called resistance, and again it represents some sort of property. So it is a property by virtue of which, because if you look in deep sense that R is having rho itself is quite deep. It is having n what is rho? Me by, and if you want to see the dependency, R depends on, of course, the tau is very important thing to discuss here. So as temperature will increase, the tau will decrease, right? Because with the increase of temperature, you will move fast. I mean, the electrons will move faster. And if you move fast, if you have more thermal velocity, your mean time of relaxation will decrease, and therefore R will increase. So resistance will grow in a value, in a way.
Sir,
And
what is tau here exactly? I didn't explain that.
tau is the mean time of relaxation. Yeah, this is tau.
Yes, okay. Yes. Thank you.
I know it's a long chapter, so long, so many formula. It is always that we will tend to forget things. So R is not technically something you're opposing. It's a property of the entire medium, which makes sure that given the applied voltage or given the potential difference or voltage, both are same, you can only establish a certain finite current or certain finite flow rate of charge. So R will restrict the I for a given V. So for a given V, how much I we can obtain, that is pre-decided by the R value. So R does not depend on potential or current. It is a vice versa. It is the R which decides what relationship between V and I will prevail. And it turns out to be that this ratio, V and I ratio, as you increase the V, I will grow, but the ratio remains same. And this ratio represents a characteristic. And this characteristic we call resistance of conductor. So the definition is very simple. What is the resistance? Let me put into some definition. Although very primary, I mean preliminary, you have studied all this in school. It's good to revisit the high school days. The resistance. So it is the characteristic of any conducting medium by virtue of which it offers opposition for the flow of charge through it. Okay, so it is a characteristic actually. So every medium, which means conducting medium, will have this characteristic, less or more, that depends on the lattice space and so on. So imagine if you have a lattice space in metal and if you want to fill those space using some carbon. So let's say we have a stainless steel, and stainless steel is so poor that although it's a, you can say, alloy of iron, but its conductivity is very poor compared to iron, because we add lots of chromium, carbon, to give it hardness so that it should not get dent easily. But a cast iron is very conductive, the router. And the steel is also very conductive. Steel is in fact the most, you can say, conductive compared to the other form of iron. And the stainless steel is not steel. Just for your clarification. So stainless, when I say stainless, or you can say rustless, so stainless steel is not steel, and therefore it is alloy actually. And we add too much carbon to give it hardness. And how the hardness is achieved? See, if you have the interspecial gaps or the voids, you fill those gaps with tiny objects, and carbon is so small that it fits those small gaps luckily. And that is why it is a choice, of a manufacturer to add carbon. And it also gets, it also helps in the reduction process. So these carbon, when go inside, they fill the gap and they restrict the movement. Okay, in a way you have less volume left for the electron to move. So those are the difficulties. So anyway, it is the characteristic of any conducting medium by virtue it offers opposition for the flow of charge through it. Let's talk about the dependency. So what is the dependency? It depends on physical property, geometrical property, and temperature. So the resistance of a conductor will depend on the physical property. So physical property means and E and R constant. So basically, tau. Oh, that's okay. So N E M. I mean, of course, this is not. This is fundamental constant. N. And geometrical means the length and area. And temperature comes from a tau actually. So physical property means the way God has defined. Geometry means the way you have defined. and temperature. The three dependency. So unit of resistance is what? And what is the dimension? So you can find V dimension, current dimension. Current is a luckily or unfortunately defined physical quantity, the fundamental quantity. And volt potential is defined as work upon charge. And charge is defined as current into time. So work is ml square t minus 2. It is I square, so we can add ampere minus 2 and time. Oh, I can multiply t there. ml square t minus 3. So the dimension of resistance you can also write. And the resistivity is closely related because resistivity is only God dependent things. It's a more intrinsic property. So you say R equals to rho into L by A. If I remove this L and A, if I remove the geometrical constraint here, then what we get is called rho. So it depends on physical property of conductor and temperature. That's it. So there is no geometrical dependence. And for God's sake, there is no dependence on voltage and current. It's a very reverse way. It is a voltage and current which or whose relation is dictated by the value R. R decides that what will be the V and I relation, not the vice versa. And that is that's like basic in disguise. So when we know that you apply V, you get current I. So by taking the ratio, you know what is the R of this entire medium. This is the formula called R equivalent. So to find the R equivalent of any medium, experimentally, what you can do, you connect the voltage, you check the current, and the ratio is actually giving you the R of the medium. Because R cannot change. No matter what V, what I you apply, R will remain same. But for every V, I will be in some proportion. And that the constant of proportionality we are calling resistance. Okay? So I'll quickly add the heading. Temperature dependence of resistivity and sorry, resistance. Both are similar. So imagine if you have a rod of resistance R at temperature theta. You increase the temperature from theta to theta plus d theta, and the resistance grows from R to R plus dr. So we define something called alpha, called temperature coefficient of, and we define in both case symbol we keep saying either resistance or resistivity. So alpha is defined as fractional change in R per unit change in temperature. That's it. What is alpha? Fractional change in resistance per unit change in temperature. Fractional change in resistance per unit change in temperature is called alpha. That's the actual definition. But you will see something really simplified. I'll show you in a while. So alpha is easy to write. It is so dr by r. We write as alpha d theta. In general, alpha itself is function of temperature. So alpha itself we write in terms of theta. So if you integrate both sides, until you do not know the alpha variation, you cannot integrate. So this is the first thing you need to know. Now, there is a special case for constant alpha. So let's say if you are varying from 30 degree to 70 degree, and if for that range of temperature alpha is not varying much, so definitely if you go from 0 degree to 300 degree, you can always see alpha is also changing. But for a small range of variation, alpha is almost same. So let's say alpha at 30 degree is same as alpha at 40 degree. So between alpha 30 to alpha 40, the alpha is roughly same. So we can treat as constant in many variety of situations. In fact, 99% question which you will face will have alpha constant, including error. Beyond that, we have alpha variable and we have some challenging question also. So once in the NEET 2015, NEET 2015, 15 not 2013. So in the NEET 2013, they asked question of alpha variable. So now if NEET can ask, so you can expect it can come in JEE-Mains also. So for constant alpha, we can take it out. And as a general trend, when at 0 degree, we write it R0, and for theta degree Celsius, we write. And it's a very famous answer. ln looks simple. alpha theta. So r theta turns out to be how much? So in general, this is the formula, which is very much exponential relation. And now comes the fancy part. Alpha is generally, so again, in general, and this is by default you have to assume also. In general, alpha is very, very less than 1. It is like 10 power minus 6 minus 5, something like that. So generally it is 10 power minus 6 minus 8 and something like that. Alpha is a very small quantity. So if you multiply with a small value of theta, let's say 80 or 100 or whatever, it is still 10 power minus 3. So it is 1,000th of a part. And we know from the expansion of e power x, we write as 1 plus so for a small value of x, if the power is very small, then we can always approximate up to the first linear term because x is very small. X square will be almost nothing. So from x approximation, we know e power x is roughly 1 plus x. Therefore, r theta will be r not 1 plus alpha theta. And this is what you will see in general in textbook, the formula. So it's a very much linear relationship. R theta equals to r not 1 plus alpha theta. And this is what you study in high school if you have kind of studied all those things. So this is the school level, but you should know that this comes from the rigorous derivation. And of course, this derivation is only true if alpha is constant. So that is also I have proved that okay, only for constant alpha you should apply this. If alpha is variable, you have to go back to this relation. Anyway, so this is important. So when alpha is variable, you know what to be done. If alpha is constant. Now, I will not do it for resistivity. You can just do the similar fashion. So for resistivity, you can add the alpha of resistivity is d rho by rho, the fractional change in rho per unit changing temperature, and everything else is same. So any doubt in this, guys? Tell me so far.
No, sir.
No, sir.
No, sir.
Some typical graph. So we have three graph, which is I'm drawing between resistivity and absolute temperature. Let's say. So you can see the graph is pretty much straight line, and then after some temperature, it starts deviating. So conductor which remains straight line, I mean, whose resistivity varies linearly in proportion to temperature. If the variation is linear, we call ohmic conductor. And in Ohm's law, we only apply for ohmic conductor, and therefore there is a range of temperature beyond this we cannot apply it, because at a very high temperature it will behave in a non-ohmic manner. And the reason is same. As the thermal becomes too much, the bulk motion will be difficult to sustain. So it's like a turbulence condition. So we have a streamline flow. Okay. So what will come out? But if the flow is too fast, then it is not streamline, it is turbulent, and things are not in control. So there is no mathematical relationship for the excessive randomness. The other is this is for conductors. So such graph is for conductors. For a semiconductor, it's very interesting. In the semiconductor, the concentration, the N value, also varies with temperature. So what happens if you increase the temperature, the N will increase, and the tau will decrease. And if you remember the resistivity formula, I mean, from conductor part, so M, mass and charge are constant, but rho is inversely proportional to N tau. So tau will decrease for sure, but N grows even much more faster than tau, and therefore the product of these two always increases. And therefore, as you increase the temperature, the resistivity actually decreases, which is very much against the idea of conductor, in which the resistance will grow with temperature. But here, in case of conductor, N is constant. But in case of semiconductor world, the charge carrier concentration itself will change with temperature. And therefore, the graph will be like this. And this is blessing in disguise. This temperature dependence of resistance has lot of usefulness when it comes to sensors. So now nowadays we have a digital thermometer. So digital thermometer is actually based on a thermal sensor, which is based on a semiconductor device. So when you put inside your mouth or armpit, the temperature will change some property of semiconductor, and that property is actually measured, which is mapped with temperature. Okay, so they know this is also, I mean, in a way, a good thing that the nuclear reactors are fitted with a large number of thermal sensors quite away from the actual reactor. So even though things are happening in the reactor, even the wall, which is, let's say, maybe 10 meters away, they receive sufficient heat, and by receiving those heat, these thermal sensors, we called TDR, temperature dependent resistors. So these TDR are very powerful. I mean, the good thing is that TDR can sustain very high temperature, and not only that, it helps in a computer, or you can say electronically stabilized nuclear reactor. So we know how much energy is generated, and we can control the reaction by pulling the rods from the reactor, okay, the uranium rods, and we can create the controlled reaction to create the controlled energy which can be harnessed. Okay, if the energy is uncontrolled, we cannot harness it. That's the problem. So that is the basis of nuclear reactor, and therefore this temperature sensitivity is a blessing in disguise. The third is superconductor. So at high temperature, they behave as bad as non-ohmic conductor. But if you go very close to the temperature, absolute zero, suddenly it drops. At very low temperature, what we call critical temperature, the resistivity drops to zero. And the reason is at such a low temperature, the lattice vibration ceases. And because the lattice vibration will almost cease, the electric field lines becomes well defined. And therefore, for the electron, it is very easy to trace that field lines without hitting anyone. And there is no vibration. So in semiconductor, the things are very unique. They are also temperature dependent, but the thing is, at high temperature, they are really bad, but they behave very strangely at a very low temperature. So the future is, and we are trying to achieve superconductivity at a normal room temperature. Because the day we are going to achieve superconductivity at this temperature, the energy consumption in the universe, the world will reduce drastically. And then the energy needs will also decrease. So we do not need so many power plants, nuclear power plants, something. In fact, the entire thing will happen almost as with zero energy. So with this, I would like to stop today's lecture. And next lecture we start the circuit. We are trying to learn the series parallel grouping and all. So in next lecture, we will see something more common which we have seen from capacitor. So till so far it was purely theory. So next lecture I will give you series parallel, and then we'll solve some of the challenging question of resistance calculation through using basic concept. It's challenging because it is not very conventional. That's why we call it challenging. Because we are like used to with V equals to IR. Okay. But we have to see V equals to IR in more scratch method, like scratch way of seeing it. More rudimentary method to solve the question. So we'll start with some 4 or 5 challenging problem, and once we are done, the rest of the questions will be similar to the capacitor, which I will skip as fast as possible. And then we'll solve some of the, again, nice circuit problems, and we'll directly go to the RC circuit. And then after that, we go to the electrical instrument, which will end this entire course, I mean, current chapter. Bye, guys. Take care. I think some of you will have some next lecture.
Thank you, sir.
Thank you, sir.
Bye, guys.
Thank you, sir.
Thank you, sir.